All right, so here we're going to start talking about some basic differentiation rules and rates of change. Okay, so the derivative, again, what it does is it's a formula that allows us to find the slope at various points. So we could use that limit definition, but we're not going to use that anymore. Hopefully we'll be using these shortcut rules instead. And they have proofs of these rules in your textbook if you're interested. All right, so our first rule is the derivative of a constant. Okay, the derivative of a constant function is just 0. All right, and that should be no surprise, right? If we have a constant function, what does that look like? Just a horizontal line, right? If this is c and we're looking at f of x equals c, we're just going to have a line, horizontal line going right through here. What's the slope of that line? What is it? 0. What's the rate of change of the line? 0. So the derivative of a constant is 0. All right, so if I have f of x is equal to -9, f prime of x is equal to 0. If we've got g of x is equal to 725, g prime of x is equal to 0. If we've got y is equal to 0, then y prime is equal to 0. Okay? Questions about that? All right, so the derivative of a constant is 0. All right?
So even if it said x equals 2, that would still be the constant and it still equals 0. It's like where it says y, that would just be.
Well, now x equals 2 would give us a vertical line, and the slope of a vertical line is undefined. Also, x equals 2 is not a function. It doesn't pass
How come
y is a function, right? We can call y is equal to f of x,
oh, okay,
right? Okay, good question. Okay, the power rule. Did I skip, or is this where I am? Okay, the power rule. And this notation right here, this is our derivative operator. Okay, there's so many mathematical operations. There are more operations than addition, subtraction, division, multiplication, raising things to powers, radicals. I mean, they go on and on and on. But this thing says the derivative of this. Okay, so when we see this, we're saying the derivative of this thing. All right, so the power rule. If n is a rational number, then the function f of x equals x to the n is differentiable, and the derivative of x to the n is n times x to the n minus 1. Okay, so what we do is we take this n that was our exponent, we bring it out front, and then we subtract 1 from that exponent. All right, that's our power rule. We'll use it all the time. Okay, so we got to get really comfortable with it. So notice here that x to the n is essentially in our numerator. Okay, so when we use this power rule, x to the n needs to be in the numerator. So in A, we've got y equals x to the 12th. Y prime is equal to 12x to the 11th. Okay, so what did I do? I brought the 12 out front, and then I subtracted 1 from my exponent. Okay? All right, in B, first of all, I'm going to rewrite this as 3x to the -7. I can't apply it until I've got it in my numerator. Okay, everybody okay with that? And then now we're going to say y prime, and we're kind of going beyond one of our rules, but just take it that this is right. Okay, the 3 I'm just going to kind of put on the side for right now. And so we get -7, bring that -7 out front, and then we have x to the -8. I subtracted 1. So we get -21x to the -8, or -21 over x to the 8th. Okay, questions about that?
So if it's negative exponent, it's just a fraction.
What do you mean it's a fraction, like it was in our denominator? We can change. Here's our algebra rule for this. If I have, let's say 1 over a is equal to, let's say to the n, is equal to a to the -n. So I can move a factor from the numerator to the denominator if I change the sign of the exponent. Okay, does that make sense? Everybody kind of remember that rule from algebra? Y'all are quiet on that one? Okay. All right. Everybody okay with that? All right. If I have, let's say, a to the -5, then that's the same thing as 1 over a to the 5. If I had 7 over x squared, then that's 7x to the -2. Okay, so we can move it from numerator to denominator if we change the factor. And we only have to move the thing that has the exponent. For instance, if I wanted to do 3 c cubed over a to the -2b, and if I said I want everything written with a positive exponent, then I would rewrite this as 3a squared c cubed b. The only one I needed to move was the a factor. Okay. All right. So this is kind of our rule for that. Okay. All right. So go back.
What if it was like a to the -5 over 3, something like that? Would you still be able to switch it and put a at the bottom?
Yes.
Okay.
I would say 1 over 3a to the 5th. All right. Okay. So we got that. Any questions about B? Okay. C. First of all, I'm going to rewrite this as x to the what? 1/4. Okay. That's another rule we need to remember. If we have the nth root of a to the m, let's say, then it's a to the m over n. So in this case, m is 1, n is 4, so x to the 1/4. All right. Now that I've got that, my derivative, g prime of x, is equal to, I'm going to bring the 1/4 out front. Okay, and then we need to subtract 1. So 1/4 minus 4/4 is -3/4. Okay. And just depending on what the directions are, we might leave it like that, or we might write that. Okay, or we could even put it back in as a radical if we needed to. Okay. And then finally for D, we've got y equals 4 over x to the -3. First, I'm going to rewrite this as what? 4x cubed, and then y prime is going to be 4 times 3x squared, or 12x squared. Yes. Did you have? Okay. All right. Questions about that? Okay. Very good. Okay. We want to practice these a lot because we'll be doing it. Now that we've kind of seen that, just to jump ahead a little bit, but we had f of x on our All right. We had f of x equals negative 5x squared plus 3. Well, instead of using that limit definition, we could say f prime of x equals negative 5. The derivative of x squared is going to be what? 2x. And the derivative of 3 is just what? 0. So that's how we could get easily negative 10x. I love that wow that I heard. Right? Well, yeah, but we needed to understand a little more. Right? So now, well, no, we still got to know how to do that. On the test, I will ask you about the limit definition. But I tell you what, on Monday, I'll give you a second chance. How about that? Huh? Which way? For the limit definition, on the test, when you see that I've asked for the limit definition, then I'll expect the whole definition thing. But if it doesn't say limit definition, don't do it. Use these shortcuts that we're talking about today. Okay? Because this is just the tip of the iceberg. We got so many other things we're going to need to be able to do with these derivatives. We can't spend all day trying to find them. All right. I've been using Theorem 2.4 already. But basically it says if f is differentiable or is a differentiable function and c is a real number, then c of f is also differentiable, and the derivative of c times f of x is equal to c times the derivative of f of x, or we could just say c times f prime of x. So that's what I was doing in the examples earlier where, what was one of them? You all let me do it. Let's say we were looking at this one. We had y equals 3x to the minus 7. Okay. So let's say we've got y equals 3x to the raised to the minus 7. All right. Then the derivative rule here says I can just bring that constant out front. Right? He just kind of goes along for the ride. He's a constant multiple. He's not added on, but he's multiplied by the function. And now I take the derivative of x to the minus 7. Okay, so we get 3 times negative 7 x to the negative 8, or negative 21 x to the 8th. So I was already doing that, but I hadn't introduced the rule for it. Everybody kind of see what the rule allows us to do? Yes, okay. If we've got a constant multiple, we can pull that constant multiple off and then apply the derivative rule to everything else. Okay. And then here's another rule. We can distribute the derivative across a sum or a difference. So the derivative of f of x plus or minus g of x is equal to, in short, f prime of x plus or minus g prime of x. So we just go right down the line when we have a sum applying these different rules. Okay, so for example, yes. Mm-hmm. Well, I left negative 8 and I forgot to write negative right here. It's still negative. Okay. You could, yes. So we could say negative 21 over x to the 8th. Well, I think it just depends on the problem. If you left it as negative 8, I wouldn't have a problem with that. When you go to do your homework in WebAssign, they may say use positive exponents. And then a little bit later, when we start needing to, factor and cancel, then that may influence what we do with it next. So it just depends on where we're going. But if that was the final answer, I don't really have a problem with that negative exponent so much. Okay. All right. So the sum and difference rules find the derivative. Okay, notice here I've got sums and differences, but that's okay. I'm just going to take the derivative of each part. All right, so we have y equals t squared minus 3t plus 1. So y prime equals what? 2t and then minus 3. Okay, now questions about that one? Okay, the derivative, let's deal with just t by itself first. Okay, of course, if we have just t, that's t to the 1, right? And so the derivative of this says we bring the 1 out front and then we subtract. So we get what? 0. And t to the 0 is 1. But I also had this constant multiple, right? So the 3 just kind of went along for the ride, right? It was 3 times the derivative of t to the 1. So we already had this 3, t to the 0 just gets 3. Okay? The, it's a constant, so the derivative of a constant is 0. Each part, that's right. We could say plus 0, but that's just 2t minus 3. What about b? Okay, y prime is going to be what? 6x squared plus 12x minus 1. Okay, questions about that? All right, very good. Okay, derivatives of sine and cosine functions. Lots of derivatives, okay? The derivative of sine x is cosine x. And the derivative of cosine x is minus sine x. Okay. So we got to remember those, all of these derivative rules, and there are lots of them. We're just kind of doing some of the basic ones right now, and you really need to memorize all of these rules, okay, and be able to apply them. All right, so in this example, g of t is equal to pi cosine of t. Okay, so which rules do you think I'm going to use? Okay, I'm definitely going to use the derivative of cosine rule. And what about that pi? What is it? It's a constant multiple. Very good. So g prime of t, okay, my constant multiple, he just goes along for the ride. And now I need to focus on the derivative of cosine t. The derivative of cosine t is minus sine t. Okay, so we get minus pi sine t. What about b? Okay, y prime is just going to be equal to cosine x because the derivative of 7 was 0. Okay. Pi was multiplied and the 7 was added. That's a great question. Okay, what's the difference between pi and 7? This pi is a constant multiple, but this 7 was added. Okay, and so we've not talked about a product rule, but we will a little bit later. But for now, if we just have a constant multiple, he goes along for the ride. If it's a constant added on, the derivative of that is 0. Okay. Okay. Now, as I just mentioned, we don't have a product rule right now. We also don't have a quotient rule. We'll be getting those soon, but for now, let's stick with what we know. Don't make up any rules, okay, unless you have tried them. But what I'm going to do first is simplify this. Okay, f of x is equal to 2x to the 4th over x cubed minus x over x cubed, right? I just distributed my denominator, okay, since I had a single term or single factor denominator, single term denominator. And so when I reduce this, this is what? 2x minus 1. Okay, 1 over x squared. Okay, 1 over x squared, we'll write it like that. Or we've got 2x minus x to the negative 2. Okay, now all of that was just algebra. I still need to find the derivative. Okay, questions? Okay. Um, well, you could think of this as canceling out. We had x to the first up here. And then if I took out 1 down here to go with it, we're left with 2. Right? So up top, we've got a 1, and on the bottom, we got x squared. Okay? The rule, our algebra rule for dealing with this is a to the m over a to the n is equal to what? A to the m minus n. Okay? That's going to be really important that we get comfortable with that, because we'll be canceling out a lot of things between our numerator and denominator. And this number, this a to the m minus n, always, always, always goes in the numerator. Okay, then if it's negative, we can move it to the denominator. Okay, so if we use that here, we would have said 1 minus 3 gives us x to the negative 2. And so then we would have moved that to the denominator to make it positive. Okay. All right, now, did I take my derivative yet? No. Okay. All right, so f prime of x is going to equal what? 2 plus 2x to the what? Negative 3. Got to go down. Okay, so 2 plus 2x to the negative 3. Okay. Or if we wanted to, 2 plus 2 over x cubed. All right, would be the right answer. Okay, questions about that? All right. All right, let's do, if we can, one more, then we'll stop. Seems like there was something. Label your functions. All right, we're going to need to come back and do different things with these functions. So please label your functions. All right, what would this look like if I just had all of this up here and no f of x, no f prime of x? Okay, label your functions as you go. All right, it's going to be important to try to keep your work organized. All right. Okay, over here, we don't have a product rule yet, so what I'm going to do is simplify by distributing x squared. So we get what? 2 fourths. Very good. Very good. Okay, so that's y. Now I need to take the derivative, and what is it going to be? What else? Minus 9x squared. Okay. All right, very good. All right, so we're still looking at the derivative and just found some very basic derivative rules last time. So in this one, the first thing I need to do before I take the derivative is what? Okay, get the x out of our denominator. So first I'm going to rewrite this as f of x equals 2 over x to the 1/3 plus 3 cosine x. And then I'm going to write it again as 2x to the negative 1/3 plus 3 cosine x. Okay, so I've not taken the derivative yet, just rewrote it so that I can take the derivative. Now, f prime of x is equal to what? Negative 2/3 x to the Negative 4/3. Very good. Okay. 1/3 minus 1. Or we can think of it as 1/3, rather negative 1/3 minus 3/3. Right? Gives us negative 4/3. Okay. The derivative of cosine is what? Very good. So this is going to be minus 3 sine x. Okay. And that's our derivative. Questions about that one? Which negative? It just depends on, what they're asking for. So if I didn't want to leave it here, I might write it as negative 2 over 3x to the 4/3. Okay, minus 3 sine x. Okay, looks like B is exactly the same. So I think we don't need to do that one. Okay, questions about this? The derivative, the derivative of cosine is minus sine x. So that was one of the rules that we looked at last time. So just, we just got to remember that one. Okay, and then the derivative of sine is cosine x. Okay. You mean you're looking at this one? Yeah, it's just an error. I must have gotten interrupted. There should have been some t's there, but that's just wrong altogether. Okay, so copy and paste. I blame that. Okay, so some more on find the equation of the tangent line. This is something we will see over and over and over again. So if you're not comfortable finding the equation of a line, you need to get comfortable because we'll see this often throughout the semester. Okay, so find the equation of the tangent line to the graph of f at the given point. So the first thing I need to do, if that's what I'm asked to find, is take the derivative. Y prime is equal to what? Okay, 3x squared minus 3. Okay, so that's our derivative. Now I'm going to use the derivative to do what? Find the slope at this point. So the slope at the point 2, 2 is going to be 3 times 2 squared minus 3. Or 3 times 4 is 12, minus 3 is 9. Okay, so I've got my slope. Now that I have my slope, the next thing I need to do is use the point slope equation. Yes, absolutely. Well, this one is cubic. But yes, no matter what the function is, the interpretation of the derivative is that it gives us the slope of the tangent line. So yes. All right. So we do y minus 2 equals 9 times x minus 2. Okay, or 9x minus 18. Okay, and that's going to be plus 2. Or y equals 9x minus 16. Okay, questions about this? We only use the x-intercept. We can only use the, well, in our formula for slope, that's the only thing we had a place to put in. A little bit later when we take derivatives, implicit differentiation, we might have x and y in our formula, and we can put both of them in. But right now, we don't even have a place to put the y coordinate. Put the value in for y prime? No, it's y prime and y are different things. Okay. Yes, ma'am.
I know it has to do with the rules, but can you explain how y prime is 3x squared works?
Okay, what I did, I brought the 3 out front and then subtracted 1. So that's how we got 3x squared.
Oh, okay.
Okay.
So with anything, you can always, any kind of, when it's raised to an x, you
Yes. Okay, that's our power rule. The derivative of x to the n is n times x to the n minus 1. Okay. All right. Other questions? Okay, what about b? Before we do anything with that, we should what? Okay, multiply, right? We're going to multiply, so we get f of x is equal to, I'm using FOIL, so I get x cubed for the first. Outer gives me plus 3x squared. Inner minus 2x squared. Last is minus 6x, right? Yeah. Okay. All right, so we get x cubed plus x squared minus 6x. Okay, that's still f of x. Now I'm ready to take the derivative. Okay, and so the derivative is what? 3x squared plus 2x minus 6. Okay, all right, so I've got my derivative, and now I need to find the slope at the point 1, negative 4. So f prime of 1, okay, that's going to give me my slope at the point 1, negative 4, is 3 plus 2 minus 6, so it looks like negative 1. Okay, I just plugged in 1 for my derivative. 5 minus 6 is negative 1. And so we can, I'm not here yet, we can say y minus y1 equals m times x minus x1. Okay, or y plus 4 equals negative x plus 1, right? Y equals negative x minus 3. Okay, did I do something wrong? Where did I get the what? This negative 1? When I plugged in 1 here, I got negative 1. So it was 3 plus 2 gave me 5. 5 minus 6 was negative 1. No, it's x squared. So 1 squared is 1. It would have to be in parentheses, right? Okay. All right, other questions about that? Okay, any? Okay, once I found the slope, then I use my point slope formula. You mean over here? No? Oh, my answer's down here, sorry. No, this is the equation of the tangent line. This is it. So if we were to graph this equation and this equation, the line should just brush this function at the point 1, negative 4. Okay, yes. Okay. Yes, I ran out of space. We're still doing we're still doing B. Yes, I ran out of space. Huh? No, it was all this thing. I just ran out of space, so I just crossed all this out. Just ignore that and that. Okay. Yes. Where did I get the negative? Yep, this is my point slope formula. Y minus y1 equals m times x minus x1. Okay. All right, other questions? Okay, everybody good? All right, very good. Okay, so got to know how to find the equation of the tangent line. That will be asked over and over and over again throughout the semester. Okay, now here's another one that we often want to do as well, and that is determine the points at which the graph of the function has a horizontal tangent line. That's going to be really important to us because it's at those points where we can have a maximum value or a minimum value. So we're going to need to know where this horizontal tangent line occurs. And we were just talking about it. If we have a horizontal tangent line, it has a slope of what? 0. Okay, horizontal tangent line has a slope of 0. So what we're going to do is take the derivative, set it equal to 0, and solve. Okay? So determine the points at which the graph of the function has a horizontal tangent line. First step, find the derivative. So y prime equals 3x squared plus 1. Very good. I'm going to set this equal to 0. Okay, and so we get 3x squared equals -1. X squared equals minus 1/3. So according to this, what would you say? Are there any solutions for x? No. Okay. So, right, there's no solutions, right? So there are no points where we would have a horizontal tangent line.
And that's because if you take a square root of that, it's can't even, it's negative.
That's right. Okay. Now let's see how that matches up with the graph. Here we got x cubed plus x. So let's see. Here's our graph. And so you see there are no places where we would have a horizontal tangent line. Do you see that? Okay, if we had a horizontal tangent line, we'd have a maximum or a minimum value, and we don't have that here. Okay? All right. Of course, in our next example, we will. At least I think we will. Okay, let's look at this one. We've got y equals the square root of 3x plus 2 cosine x. Okay, so again, first step is going to be what? Find the derivative. Okay, so our derivative is what? Y prime equals square root of 3. Very good. Does everybody agree? Okay. All right, which part is maybe confusing about this? Okay, square root of 3. Okay, so, square root of 3 is a number just like 5x is a number, right? The square root of 3 is the coefficient on x, right? And x is just to the first power. So we just said square root of 3.
What if the x had been under the radical 2?
If it was under the radical 3, you mean?
Yeah, if it was under
Then I would have brought it up and said x to the -1. Okay. All right, everybody okay now with square root of 3? Is that okay? Yes, no? This goes back to our derivative rules. Okay, we said the derivative of x to the n is equal to n to the x raised, or rather n times x to the n minus 1. Okay, so for x alone, and this is worth making a special note somewhere. If we want to talk about the derivative of x to the first, according to this thing, we bring the 1 out front, and then we subtract 1 from our exponent, which is what? Okay, the exponent is 1, so 1 minus 1 is 0. X to the 0 is what? 1. So we get 1 times 1, or 1. Okay, so in short, the derivative of x to the first is just 1. All right. Last week we also said the derivative of a constant times a function is equal to c f prime of x, right? That was one of our rules as well. So basically that says if I have a constant multiple times my function, I just slide it over to the side and then I deal with the rest of it. So example, the derivative of 5x, well, I just kind of move the 5 over to the side and find the derivative of x. 5 times 1 is just what? 5. Okay. And so for us, we were looking at the derivative of the square root of 3 times x. Okay, well, square root of 3 is a constant multiple. He just kind of goes along to the side. The derivative of x is 1, so we get square root of 3.
What if it was like square root of 3x squared?
Then if it was square root of 3x squared, I would bring the 2 out front and then subtract 1, from my exponent. Okay, and that's what we're doing.
Still keep the square root of 3 as square root of 3.
It would be 2 root 3.
Okay, because
We would have multiplied it by 2
square root of 3 out.
over to the side. That's right. Okay. All right, questions about that?
I just didn't realize that the x wasn't underneath the radicals.
Oh, okay, gotcha. Okay, very good. Okay, so we got our derivative, right? Now we need to know, we're trying to find these horizontal tangent lines, so I'm going to set it equal to 0. And so we get root 3 equals 2 sine x, or sine x equals what? Root 3 over 2, okay? So between 0 and 2 pi, where is sine x equal to root 3 over 2? Pi over 6 would be 30 degrees. So pi over 3 in the first quadrant. Which other quadrant is it going to happen in? Where else is sine positive? Second quadrant. So it's going to be at 2 pi over 3. So at those two places, we would expect to see a horizontal tangent line. Okay, questions about that? Okay, let's look at a picture.
Otherwise, keep it as form of radians instead.
Yes, one, it's listed as radians here. 2 radians are real numbers, and degrees are not. Okay, so. All right, so let's look at the graph real quickly. Root 3x plus 2 cosine x. Ooh, that's interesting. All right, let's see. I'm going to zoom in a good bit. Oops. Yeah. Okay. All right, so notice here, this would be where I would have a horizontal tangent line. You see it was increasing. It starts to decrease. So in between, we learned last week or the week before, in between positive and negative, we have to go through what? 0, right? So you can see here that we would have a horizontal tangent line. Does everybody see that? Okay. So pi over 3, and then we also said at 2 pi over 3, so that's right here. Okay. Questions about that? How to find horizontal tangent line? Yes.
Because this is a continuous line, you wouldn't have to do the plus the integers.
Well, it gave us a particular range to look at. So it said, but for x is between 0 and 2 pi. Otherwise, yes, we'd have infinitely many solutions. Okay. All right, any other questions? Okay, very good. All right, rates of change. Okay. So we'll often talk about S of t. And S of t equals the position of an object at time t. Okay. Often S of t is written as, we saw this earlier in the problem, one of the homework problems that we looked at. S of t equals 1/2 gt squared plus v naught t plus s naught t, where it says the value of g on Earth is approximately negative 32 feet per second per second. And this is the acceleration due to gravity. Okay. And then v naught represents our initial velocity. Okay, we call this v naught, like K-N-O-T. So v naught is initial velocity, and s naught is going to be the initial height of our object. Okay, so for instance, notice here, it says at time t equals 0, a diver jumps from a platform diving board that is 32 feet above the water. Notice that this 32 is right here. Okay, it's the S naught in our equation. All right, and then it says the initial velocity is 16 feet per second. So that's how we get this coefficient right here. Okay, so V naught is initial velocity, S naught is the initial position. Okay, so this is a pretty general form for our position function. All right, and then what else did they say about, flip back over. Okay, that's that. All right, so yeah, right here is where you'd put the general form for S of t is going to be 16t squared plus V naught t plus S naught. Okay, and I'm not sure what I put that other blank there for. Okay, here we've got the change in position. Okay, so if you're at this position at time t plus delta t, and another position at time t. So we calculate a change. Does that make sense, that formula? This is just like saying S of 5 seconds minus S of 3 seconds. There'd be some change in position, right? So it's just one way of writing it, where delta t represents the amount of change in the time. Yes. Okay. And so our average velocity is going to be delta S over delta T. Okay, we talk about average velocity all of the time. Yesterday I had to go to Charlotte. Okay, and it took me, let's just say it took me 90 minutes. All right, and Charlotte is about what? 90 miles, right? So we could talk about my average velocity. My change in position would be 90 miles, and the time that elapsed, or the change in time, is 90 minutes. So we could say my average velocity was what? A mile a minute, right? That's the average velocity. Does that mean that I set the car so that I would go a mile a minute at 60 miles per hour? Is that how I did it? And I stayed right there? No. Okay, you slow down, you speed up, you go a little bit faster, you take some chances, and then when in the places where they say watch out, you slow down and you're a little more cautious. But that would be my average velocity, right? Okay, so S of t plus delta t minus S of t all over delta t. Okay, average velocity. But what if I had a function somehow that really did track my position all the way? Okay, somehow it did it even though I don't have this linear position function. Well, we can find instantaneous velocity, how fast you're going at any particular rate or at any particular time. Okay, the instantaneous velocity is going to be found using the derivative of our position function. Okay, so S prime of t is equal to, I guess if we wanted to do it in general, minus 32t plus v naught. Okay, but most importantly, if I want to find velocity, we just take the derivative of the position function. Okay. In general, the interpretation of the derivative is the rate of change. So if we're talking about a slope, slope is what? A rate of change of a line, right? If we're talking about velocity, it's the rate of change of your position, right? So if I take the derivative of my position function, okay, then that's going to give me velocity, all right? So don't forget this. If we want to find velocity, take the derivative of the position function, all right? So it says find the average rate of change of the function over the given interval, and then compare this average rate of change with the instantaneous rates of change at the endpoints of the interval. Okay? So if I want to find the average rate of change, it's going to be f of 3.1 minus f of 3 divided by 3.1 minus 3. Okay, so it's the change in f over the change in t. All right. And so I've got to actually plug this into my calculator. Okay, 3.1 squared minus 7 minus 9 minus 7 is 2. Okay, and then we're going to divide this by 0.1. Okay, I get 6.1. Okay. Okay.
Is it because we plug in the 3.1 for the t,
Yes.
and then we get an answer, and that's how we get the top answer?
Well, then we also have to plug in 3 and then subtract the 2.
Can you please like write out what you did
Yeah,
later?
I'm,
I'm sorry.
I'm confused at how the f of 3.1.
Kind of the same thing we did on the quiz.
No, I just plugged it in. Let's see.
So you would always go,
Yeah, we're just evaluating the function at 3.1. So Our function is t squared minus 7. So I said 3.1 squared. Oops, got 2 decimal points.
Oh, okay, because the functions that we put in.
Minus 7. And I got 2.61. And then if we put in 3 squared minus 7, we get 2. So 0.61 divided by 0.1 gave us 6.1. Yes,
Would it just be easier to cancel out the -7?
you could. I mean, however you get to it, because this part is really arithmetic. So hopefully we're all okay with that.
Be, um, like, X would be the first one and Y would be the second one.
In this interval?
Yes.
No, no, no. This is an interval. So both of these things are t-values. So we're looking at the average rate of change from 3 seconds to 3.1 seconds. So I put in 3 for t, well, 3.1 for t, and I evaluated my function. And then I put in 3 for t, and I evaluated the function. So when I put in 3.1, I got 2.61. Is that right?
I understand that, but I guess my question is why did you put the 3.1 function first and minus
Okay.
the 3.1?
Because, yes, absolutely. Because we were doing, this one would be f of t, and this is f of uh, t plus delta t.
Okay.
So that's my second time. So we would go from the highest time, well, we're going to subtract the position from the first time, of the first time from the second, okay, to get the change.
3.1 comma 3, then it would be
It wouldn't be 3.1 comma 3 because this is an interval, and in our interval notation it goes from lowest to highest always. That's right. Okay, and then this is delta t, except I wrote it out. I wrote, basically t1 or t2 minus t1.
How do you know what's delta t and what's t plus delta t?
Delta means the change in values. So delta t is just this whole change in between my t values.
How do you know at top which one's the plus and which one's just the rate of t?
Both of these represent t's, except instead of us saying t1 and t2 like we, would have said in algebra, we say t and delta t. So I had a t value at 3, delta t is 0.1. So that's how I can express 2 different points. So, yeah.
Are we always going to put the y value first and the x value second?
These are not x's and y's. Both of these are t's. So you could think of this as t1 and t2.
You always put a t2 first?
Yes.
That's not
Yeah, you put the larger one first.
See, that's what I was trying to figure out.
larger.
So it's the larger one that goes first?
But it's always going to come second anyways.
Right. Because this is interval notation. So in interval notation, you always write that with the smallest number first and then the largest number second. Okay. So this is an interval. So we're finding the average rate of change from 3 seconds to 3.1 seconds. Okay. Is that okay? All right. Okay. All right, so we found the average rate of change. All right. Now they wanted us to find the instantaneous rate of change. And so to do that, I'm going to take the derivative. Okay. So f prime of t is equal to 2t. And I can use that to find the rate of change at any point in time for this function. And so they said do it for both endpoints. So f prime of 3 is equal to what? 2 times 3 or 6. And f prime of 3.1 is 2 times 3.1 or 6.2. Okay. Yes.
Where are you getting the f of prime t equals 2t?
Okay. F of t was t squared minus 7. I took the derivative of that. Okay. And that's why it's going to be really important that we label our functions. Okay. A little bit later, we're going to have f double prime, f triple prime. You can have the fifth derivative, the 10th derivative, and you need to label those things because we'll be looking back and forth at them. Okay. Other questions? Okay. So average rate of change. Pretty straightforward, I think. Yes.
Can we always expect both of them to be similar as a mean?
Not necessarily. It just depends on, which points you pick. It just, yeah, that's all. Just like, I don't know, the answer is no. Okay. For instance, I guess an extreme example might be if we look at time 0, if the process is starting at that time, then you might not have any speed or position at all, right? And then you look at, down the road 10 minutes, then there's going to be a huge change in those, okay? So, no. All right, other questions? All right, very good. Just like, did anybody come to school this morning at about 8 o'clock? Did you come? 8 o'clock? And there was an accident on Airport Boulevard. The traffic was backed up on I-26. It was very frustrating. So, can we average that with, what we hope to have this afternoon? Not exactly. They don't exactly balance each other out. So, yeah. All right, very good. Okay. A ball is thrown straight down from the top of a 220-foot building with an initial velocity of negative 22 feet per second. What is its velocity after 3 seconds? What is its velocity after falling 108 feet? Okay, so before we can talk about velocity, we need to know what the position function is. And we were just saying a little while ago, this is something that you should probably commit to memory. Our position function, S, is equal to negative 16 t squared plus v naught t plus s naught. Okay, that's our general position function. Okay, put a star next to it, highlight it because you need to know that for the test. Okay. And so now I can get a little more specific with this. It tells me that the ball is thrown from the top of a 220-foot building. So 220 feet is going to be what? S naught. Okay, my initial position. So I got negative 16 t squared, okay, plus 220. Okay, and then I have an initial velocity of negative 22 feet per second. So this is going to be what? Very good. Okay, so this is now my position function for this scenario. Okay. All right, we've got 2 questions. What is the velocity after 3 seconds? Okay, well, to find the velocity, what am I going to do? Nope, we got to do something else first. Take the derivative. Okay, v of t is the derivative of the position function. Okay, so in this case, negative 32t minus 22. Okay, now if I want to know the velocity after 3 seconds, I can say v of 3 is equal to negative 32 times 3 minus 22. All right, I get negative 121. And we should use units if we know them. Negative 121 what? Position was measured in feet, and the time is seconds. Okay.
I got 118.
Really? Okay, what'd you get? 118. Okay. Oh, I put in 33 instead of 33. Okay, so negative 118. Very good. Okay, negative 118 feet per second. All right. So then it says, what is its velocity after falling 108 feet? Okay. Well, I don't know when it reaches that height. Okay. So first of all, I got to figure out how long does it take it to fall 108 feet. Once I figure that out, then I can just plug that time into my velocity function. Okay. Does that make sense? Okay. So our initial height was 220 feet. Okay, this is kind of a part B here. Okay, so if I fall 108 feet, what height would I be at? Okay, 220 minus 108 is 112. All right, so if I fall 108 feet, that means the height is 112 feet. I need to figure out how long it takes for that to happen. So we're going to say negative 16 t squared minus 22t plus 220 equals 112. Okay, and we got to solve this. So what I'm going to do is subtract 112 from both sides. When I do, I get what? 108. And how can I solve this? Okay, it's a quadratic equation, so I'm going to use the quadratic formula if I don't know how to factor it. Okay, so quadratic formula, if you're not familiar with that, put that on your list of things to refresh. X equals minus b plus or minus the square root of b squared minus 4ac all over 2a. Okay. Or x equals, okay, in this case, b is negative 22, so we get 22 plus or minus the square root of negative 22 squared minus 4 times negative 16 times 108 all over 2 times negative 16. Okay, so we're going to put this in our calculator. All right, I got 2 is one of them. Anybody else get 2? Yes? No? Okay. All right, I got 1 nod. And if I do the plus, okay, we get negative 3.375, right? So one of these answers isn't feasible, right? Okay, negative 3.375 doesn't make sense. We cannot have negative time. Yes? Everybody come with me? All right, good. So I'm not even worried about negative 375. The only one that makes sense would be 2. Okay, at 2, the position function would be, or the position of the object would have fallen 108 feet. So to figure out the velocity, I'm going to look at v of 2. So, and go back to our velocity function wherever it is. Looks like it was negative 32t minus 22. Is that right? So we get negative 64 minus 22 would be negative 86 feet per second. Okay. Questions about that? About any of that?
How come you get 108 or 112 for STD?
Okay, we started at the top of this building, which was 220 feet, and we want to know the velocity after it has fallen 108 feet. So I took, we were at 220. If I fall to 100, or if I fall 108 feet, what's the new height of the object?
Be 112.
Right, so that's why I put my position equal to 112. And then so I took the position function and set it equal to 112, and we solved for t. I put x, but t.
What was your answer?
For my final, it was negative 86 feet per second. Is that okay? Okay. Are you okay? Okay. All right, other questions about this? Okay. All right, there's definitely one in the homework like that because we kind of saw it earlier today. All right, now, if the problem, Mr. Foglia had said, what's the velocity when it reaches a height of 108 feet, then I would have just said S of t equals 108. But it says, what's the velocity after it has fallen 108 feet? So I had to figure out what that new height was. I don't know if that's where you might have been.
I was thinking you just plug the 108 right in where the 220 is.
Into right here?
Yeah.
Well, 108 is, yeah, it's the position, it's not a time. Okay. All right, any other questions about this? Okay, very good. Okay. To estimate the height of a building, a stone is dropped from the top of the building into a pool of water at ground level. The splash is seen 5.6 seconds after the stone is dropped. What is the height of the building? Okay. All right, so we got some interesting stuff here. We know we need what kind of a function? What is it? We're talking about the position function, right? Because we're looking at the height. So I'm going to at least start with my general formula for position. Okay. All right, what else do we know about this thing? Okay, we know the time that it takes for what to happen? For it to hit the ground. Okay, so we know basically that S of 5.6 should equal 0. Okay, S of 5.6 equals 0. All right, because it takes 5.6 seconds before we see the splash. Okay, and what else do we know? One other thing we know. Yes. The initial velocity is 0, right? Okay, if you're the, what is it, menace who decides to do this, or maybe you're the young scientist who decides to do this, at the beginning of your process, the velocity of the object is 0, right? It's not moving. Then you drop it, and then there it goes. So V naught, okay, is going to be 0. So we can come up with a better model. It's negative 16t squared plus S naught. Okay, we don't need V naught. V naught is equal to 0 because at the beginning of this process, the object is, really at rest. It's not moving. Okay, so now that I know that, that makes this a little bit easier to solve. If I plug in 5.6, I should get out what? 0. Okay, so I'm going to do negative 16 times 5.6 squared plus S naught equals 0. Okay, S of 5.6 is right here. And then we want that to be equal to 0. Okay, so I think it's pretty straightforward from there. Okay, I get negative 501.76. Okay, plus S naught equals 0, or S naught equals 501.76. And I'm guessing this was feet. Okay. All right, questions about that? So that was really more about understanding the position function. We didn't even take a derivative or anything. Okay, what about this one? The area of a square with the sides of length s is given by a equals s squared. Find the rate of change of the area with respect to s when s equals 6 meters. Okay, so we've got a formula for area. Area is equal to s squared. Okay, and so rate of change, when I hear find the rate of change, I'm going to do what? No, take the derivative. Okay, almost every problem from here on out is going to start with the derivative. Okay, so, but definitely if you're talking about rate of change, we want a derivative. Okay, so A prime is going to be 2s. Okay, that's going to give us the rate of change of the area. Okay, and so how fast is area changing when the sides are of length 6? We would say 2 times 6 or 12. And again, they didn't give us, or it does say meters, right? So this would be 12 meters squared per, is it second? It doesn't say. So per unit of time. All right, unit of time. Okay. Questions about that?